Welcome back, students. Let's review what we know about absolute value inequalities. First, we should establish what absolute value means. Absolute value means distance from zero. We're going to use that fact often in these problems. Here are the two basic absolute value inequality problems. For each one, we're to solve, graph, find the interval notation. What does this really say? Absolute value x is less than 5. But absolute value means distance from 0. So this really says, can you show me all the numbers whose distance from 0 is less than 5? All the numbers that are closer to 0 than 5 is. Let's show that on a number line. Here's 0. I'll put positive 5 here and negative 5 here. And let's cover up all of the numbers that are closer to 0 than 5 is. Numbers that are closer to 0 than 5 would be like 4 and 3. Also negative 4 and negative 1. All the numbers between negative 5 and 5 are closer to 0 than 5 is. All of these numbers in here satisfy that absolute value inequality. Now, what numbers did I just cover up? I covered up all of the numbers that are between 5 and negative 5. Between 5 and negative 5. Absolute value inequalities that are less than become between problems. As an interval notation, that would look like this. All of the numbers from negative 5 up to 5. Let's try this one. Absolute value greater than or equal to 3. Now, what does absolute value mean? Absolute value means distance from 0. Can you show me all of the numbers that are greater than 3 away from 0? Can you show me all of the numbers that are more than 3 away from 0? Let's show that on a graph. All of the numbers that are more than 3 away from 0. Let's put 0 here. There's positive 3. There's negative 3. What are the numbers that are more than 3 away from 0? That would be like 4 and 5 and 6. Also, negative 4 and negative 5 and negative 6 are also more than 3 away from 0. All of the numbers to the right of 3 and all of the numbers to the left of negative 3. Now this problem also has an equal bar here, which means I want numbers that are equal to 3. Since absolute value means distance from 0, negative 3 also has a distance from 0 that is equal to 3. When we did this one back here, no equal bar. So we don't want the 5 and the negative 5. Leave the dots open. When you have an equal bar, we want those dots. Now, what have we covered? What we've covered are numbers that are to the right of 3 or equal to 3. We've also covered numbers that are to the left of negative 3. Anything that is to the left of negative 3 or that is to the right of positive 3 will make this inequality true. As an interval, this part of the graph covers up everything from negative infinity to negative 3. The strong bracket shows that we want the 3. Or we've also covered up all the numbers from 3 to positive infinity. So when you're working your homework problems, here's the way your answer should look. Solve, graph, interval notation. Let's try a more complicated problem. I've got my basic example here. We'll keep that as notes and refer back to it. Here's what a homework problem might look like. First thing I notice is its absolute value less than. Well, I know that absolute value less than becomes a between problem. Let's rewrite this as a between problem. I want x plus 5 to be between 7 and negative 7. Now let's solve for x. If I want to get x by itself, I must get rid of this 5. The inverse of addition is subtraction. So we'll subtract 5, but we must subtract 5 everywhere. Positive 5 and negative 5 is 0 plus x. 7 minus 5 is 2. Negative 7 and negative 5 is negative 12. There's my solve. Now let's graph. For my graph, here's 0. Negative 12 would be down here. 2 about there. What am I supposed to cover up? I'm supposed to cover up all the numbers between negative 12 and 2. All of the numbers between negative 12 and 2. And since I've got equal bars, we'll color in those dots. There's my solve. There's my graph. Now for my interval notation, I've covered up everything from negative 12 to positive 2. The strong brackets show that I want the negative 12 and I want the positive 2. Let's try one more example. This one looks pretty complicated. Here's my basic example for when you have absolute value greater than. We'll keep this here so we can refer back to it. What have I got? I've got absolute value greater than, but I've also got this extra 5. I can't start through this process until I get rid of that 5. Let's get rid of a positive 5 with a negative 5. Positive 5 and negative 5 is 0, leaving me with absolute value 4x plus 1 greater than 11. Now, absolute value greater than, I know absolute value greater than becomes an or problem, where I'm either to the right of the positive number or to the left of the negative number. I want 4x plus 1 to be to the right of 11, or I want 4x plus 1 to be to the left of negative 11. Now let's solve. In order to get this x by itself, we'll subtract 1 from each side. And divide by 4. Let's use the same process here. We'll subtract 1 from each side. And divide by 4. Ten divided by 4 is 2.5. There's the solve. Now let's graph. Here's 0. Here's negative 3. Here's positive 3. What do I want to cover with my graph? I want to cover numbers that are smaller than negative 3. That is, to the left of negative 3. I also want to cover numbers that are to the right, bigger than 2.5. 2.5 would be about there. There's no equal bars, so we'll leave the circles open. As an interval, what have I covered up? I've covered up everything from negative infinity to -3. Or I'll also cover numbers from 2.5 to positive infinity. The soft brackets, the soft parentheses, because the circles are left open. Had the circles been closed, that's when we use the strong brackets. All right, your turn. Go work some homework problems. I'll see you later on today.